Human history is told by the energy we use. At first, we had to use our muscles, then we learned to control fire. We industrialized the world using coal and oil and entered the atomic age when we learned how to split a nucleus. At each step, we increased our energy harvest to a scale never seen before and advanced as a species. Currently, we're slowly transitioning to renewables, and if we're lucky, fusion energy will become viable in the future. As humanity progresses further, if we don't destroy ourselves or our habitat, we will likely gain complete control of our planet's resources. At that stage, we'll probably begin to look outwards for new places to expand into. But space is hard, and establishing a serious human presence in the solar system will require ungodly amounts of energy. Luckily, we know where to find it. The Sun, the ultimate source of energy. A furnace 100 quintillion times more powerful than our most efficient nuclear reactor. It shines with the energy of 1 trillion nuclear bombs per second. So how do we get this energy? Not some of it, all of it. If we want to collect the most energy physically possible, we'll have to build the largest, most ambitious structure in the universe, the Dyson Sphere, a megastructure that encompasses a whole star to capture its power output. For an intelligent species, building a Dyson Sphere is a technological leap on a par with the discovery of fire for our ancestors. The transition from a planetary species to an interstellar species. It would usher in an age of exploration and expansion on a scale we can barely imagine. So, what would it look like? A solid shell enveloping the Sun is probably not the way to go. A large rigid body like that would be vulnerable to impacts, possibly shattering. It would be liable to drift and could crash straight into the Sun. A more viable design for a Dyson Sphere might be a Dyson Swarm, an enormous set of orbiting panels that collect the Sun's power and beam it elsewhere. Such a swarm would give humanity basically unlimited energy. But building it won't be easy. The Sun is very big, so we need a lot of satellites. If each satellite is a square kilometer, we'd need around 30 quadrillion to surround the Sun. Even if they're built as lightly as possible, we need about 100 quintillion tons of material. And then we need the energy to actually put the parts together and deliver them to their positions around the Sun. On top of all that, we need to have a permanent infrastructure set up in space to start building. Let's assume for the purposes of this video that our descendants will take care of that and want to create the megastructure. We can sort the challenges into 3 main categories: materials, design, and energy. To get the vast amounts of raw materials required for our Dyson Swarm, we'll have to largely disassemble a whole planet. Of the planets available, Mercury is the best candidate. It's the closest to the Sun and very metal-rich. Close to the Sun also means less moving stuff around. And Mercury has no atmosphere and only about 1/3 of the surface gravity of Earth, making it comparatively easy to launch material into space. Next, we should consider the design of our swarm. Simpler is better. Conventional solar panels are far too intricate and short-lived. Our satellites need to operate without repairs or intervention for astronomically long times, and they need to be cheap to produce. They're most likely going to be enormous mirrors, which refocus sunlight to central collecting stations like in concentrated solar power on Earth. To build and launch them efficiently, they must be incredibly light, made of little more than polished metal foil bound to some supports. And last, we need the energy to build and launch the swarm itself. Taking apart a planet and launching things into space requires an enormous amount of energy. For example, if we used all the fossil fuels and uranium on Earth and we were perfectly efficient, we could only launch as much mass as Mount Everest into space. A rather meager accomplishment compared to planetary disassembly. To get the energy needed to build a Dyson Sphere, it's almost as if you're going to need the power output of a Dyson Sphere. But that's okay. There's plenty of sunlight to be had on Mercury, so let's get to work. Humans are expensive to keep alive and are very sensitive to the environment, so we'd want to automate as much as possible. Ideally, we'd have a small crew of controllers who oversee an army of autonomous machines doing the actual work. There are 4 major pieces of technology required: solar collectors, miners, refiners, and launch equipment. The solar collectors are going to give us the energy we need to disassemble the planet. To start, maybe we deploy something like 1 square kilometer of them, either as mirrors or as traditional solar panels. They'll provide the energy to run our miners, which strip mine the surface of the planet, and our refiners, which extract valuable elements and fabricate them into our swarm satellites. To get them into space, we need a creative and efficient solution. Rockets are too expensive and difficult to deorbit and reuse. Instead, we'll want to use a sort of railgun, a long electromagnetic track which launches our satellites at high speeds. Our swarm satellites would be packed tight for launch, unfurling like an enormous origami once in orbit. From this point, we can take advantage of exponential growth, using the energy of the existing parts of the swarm to build more infrastructure on Mercury and launch new panels faster and faster. Each panel provides the energy to build another. Those 2 work together to build the next 2. 4 become 8, 8 becomes 16, and so on. Within just about 60 doubling times, the Sun would be completely surrounded by solar panels. And this can happen quickly. If a square kilometer of solar collectors takes a month to build, we could be done in a decade, if only our infrastructure on the planet's surface can keep up with the quickly growing budget of energy. Even collecting 1% of the Sun's energy is an unbelievable change in our species' energy budget. We could create the infrastructure to beam basically unlimited amounts of energy around the solar system for all sorts of projects. Colonies on other worlds, terraforming planets, constructing more megastructures, or even traveling to other stars. It could be the start of an interstellar civilization. Based on physics alone, this is not just possible, but easy. It's such a simple process and such a necessary step for any species to expand beyond their home planet that many astronomers think there are probably Dyson spheres already out there in the Milky Way. We haven't spotted any yet, but they could be there. It's far from certain that humanity will ever get to this point. Our attention is too often focused on short-term political gains and conflicts that will not matter in the long run. But if we survive the challenges we've set ourselves, we could potentially become the first species in the universe to create a structure with the scope of a star. If we do it, the only limitation left will be our own imagination. Could aliens destroy us from light years away? Another day at the Kurzgesagt Labs, where we answer the most important questions with science. Today, how might civilizations wage war across light years? What kind of devastating weapons could they use? And what would they look like? Meet our 2 players, a yellow dwarf star system home to a species of primates. Humans, as they call themselves, recently became a technological civilization. They have rockets, nuclear reactors, and memes. How cute. The Smorpions disagree. They reside on a planet around the orange dwarf star HD 40307, 42 light-years away. Smorpion civilization developed earlier than humans, and they have much better technology. They've recently built a Dyson swarm around their star, which gives them near limitless energy. And they noticed humanity, which is unfortunate as the Smorpions are planning a hyperspace bypass through our solar system. So they decided that humanity has to go. Interstellar war is hard though. Front lines, tactics and logistics are meaningless at these scales. It's also fought across time. Decades will pass between firing a weapon and learning whether it hit or not. Sending an invasion fleet is futile. Even if the Smorpions travel at a large fraction of the speed of light, the journey to Earth would take decades or even centuries, and humans would have plenty of time to prepare. If you want to learn more about the mind-numbing problem of war between alien civilizations, we made a video about it. Today, we'll help the Smorpions construct a weapon that is not only extremely long-range and as fast as physically possible, but that will totally destroy everything on Earth, so no human survivors will come to enact vengeance on Smorp in the future. In interstellar war, you want to win with one shot. Our bird scientists have found 3 Smorpion designs: the star laser, the relativistic missile, and the ultra-relativistic electron beam, all based on real technologies that humans are using in some form already. Let's see how they work. The star laser. As an advanced technological civilization, the Smorpions harness the energy of their star by surrounding it with billions of solar power satellites. This Dyson swarm collects 1% of the star's energy output, 1,000,000 billion watts, 50 billion times more than all humanity generates. What if all the power of the Dyson swarm, all those satellites, were used to create a star laser? Like any laser, the bigger it is, the longer its range. Human-built lasers use small mirrors to focus, so they have short ranges. The Smorpions could turn their entire Dyson swarm into a collective focusing element 1,000,000 kilometers wide. The star laser has an insane range as a result, enough to focus on target Earth from a distance of over 2 million light-years. Okay, let's shoot it. Countless tiny beams combine into a single huge beam. Laser beams are normally invisible in space, but the star laser is so powerful that light scattering off bits of dust and gas in its path makes it clearly visible in the sky. A gigantic column of green light. The laser travels at the speed of light, which oddly enough is still pretty slow on a galactic level. It takes a whole day until the laser has left the Smorpion system, shooting into the emptiness between stars. It will travel for decades, occasionally melting the odd bit of interstellar dust or asteroid. 42 years after being fired, it arrives without warning. Humans only notice a weird green glow in the sky, and then they're gone. 1% of the energy of a star concentrated into a beam the diameter of Earth, traveling 42 light-years. It burns the exposed half of the planet with the intensity of 3 million suns. The seas boil and evaporate, fires scour the land, and within minutes, Earth's crust begins to melt into a sea of lava. As the planet rotates, it turns into a red-hot hell with no trace of life. After a day, it's all over and the laser dies down. In another 42 years, the Smorpions will know if they've been successful. That's another thing about interstellar war. When you attack, your grandchildren will be the ones to find out if you won. It's like all the bombs from World War II exploding in the 80s and us only seeing the effect today. Okay, the star laser's extreme range, speed of light attack, and ability to melt down any target make it a premier interstellar weapon. But is there something else? The relativistic missile. What if, instead of converting the energy of their Dyson swarm into a laser, the Smorpions used it to shoot a super bullet? A relativistic missile, going as close to the speed of light as possible. This sort of weapon is at the limits of what the Smorpions' technology can handle, as it requires loads of a highly dangerous material, antimatter, the evil twin of regular matter. Humans have only managed to produce a few nanograms of antimatter. With their unlimited energy, Smorpions can manufacture it at an industrial scale to build antimatter rockets. When antimatter and matter are mixed, they annihilate, which in more practical terms means there's a big boom releasing gamma rays and plasma. The physics is complicated, but basically, if you have a really strong magnetic field, you can deflect the plasma through a nozzle, just like in the chemical rockets humans use. But it would be much faster. The fastest rocket possibly, basically. Our relativistic missile is much bigger than a skyscraper. At the bottom is the bell-shaped magnetic nozzle 100 meters wide. On top of it are 250 floors filled with antimatter and matter ready to annihilate each other. On the top floor is a 300-kilogram projectile looking quite small, about the size of a person. To stop them getting damaged on the way, the missiles have dozens of sacrificial layers that form a Whipple shield. To make sure they do their job, the Smorpions build 1,000 missiles. Let's fire them. Launching all the relativistic missiles is a spectacular event. For a moment, the antimatter engines lighting up outshine their star. Their exhaust is a long trail of brilliant white, and as they accelerate away, they appear redder and redder until they turn invisible. With the extreme amount of energy released by the matter-antimatter reactions, the missiles are accelerated to 99.9999996% of the speed of light. They have effectively infinite range, as there's nothing really to slow them down. They arrive shortly after you can see them. The light from their launch will take 42 years to reach Earth, so human astronomers might see the flash of the missile's launch, and then a few days later, they'll hit. Not enough time to prepare. Each relativistic missile packs the kinetic energy of a dinosaur killer asteroid, so only one needs to hit. They never reach the ground, disintegrating instead at the edge of Earth's atmosphere. Intense blue flashes set everything on fire. Then continent-sized fireballs slam down on the surface to smash everything into dust, repeatedly, until nothing is left but rubble and smoke. So interstellar missiles with unlimited range, minimal warning, and delivering complete destruction of a planet's surface. Nice. But they are a hassle to build. Is there something else, maybe? The ultra-relativistic electron beam. Humans do funny things to their food to rid it of bacteria and make it safe to eat, like shooting electron beams at strawberries. Small particle accelerators send electrons into the food with an energy similar to the radiation from nuclear reactions. Not enough to burn the food, but deadly to bacteria. Scorpions had the same idea, but bigger. The main challenge with an electron beam is range. Electrons are negatively charged particles, so they don't want to stay near each other. A regular electron beam will quickly spread out, making it harmless. Scorpions need it to cover distances of dozens of light years. So they've used the rules of the universe to trick the electrons by building an ultra-relativistic electron beam, or UREB. What it does is accelerate the electrons to 99.99999999999999999999999999999% of the speed of light. Faster than even the most powerful cosmic rays. The closer something travels to the speed of light, the slower time moves for it relative to the rest of the universe. And since these electrons are moving so incredibly fast, for every second of spreading they experience, over 5 million years pass in real time. A physics trick that lets the beam cross interstellar distances while remaining tightly focused on its target. The biggest particle accelerator on Earth is 27 kilometers long. The Scorpions need one that's over 100,000 kilometers long, a megastructure 8 times longer than Earth is wide. It's mostly a tube of magnets holding the beam together until the exit. Like a long trumpet of doom surrounded by an aura of deadly radiation. When it's fired, it produces a ruler-straight lightning bolt pointed at Earth. Its effects on arrival are less visible than the other weapons. No flashes of light, no massive firestorms, no explosions. It doesn't destroy rocks, it destroys DNA. People get dizzy, then fall sick as their cells are pierced by radiation. You might think that a deep bunker could save a few humans, but no. The UREB is so penetrating that its effects accumulate to lethal doses even underground over days or weeks. In the end, just like our strawberries, Earth becomes sterile. Simulation results. Another elaborate animated science explainer by Kurzgesagt, where we've learned a lot, not sure exactly what. Luckily, the Scorpions don't really exist, but others might. One major downside of all our weapons is that others around the Milky Way could see you firing them, which is not ideal because you don't want to present yourself as a dangerous species and tell everybody where exactly you are. So maybe instead of shouting or shooting out into the universe, the best course of action seems to be to stay relatively quiet for now and observe. Maybe one day we'll witness distant stars shooting at each other and be glad we stayed out of it.
Flight mode.
Expanding our transportation build additional interstellar logistic stations. So now I am
Insufficient materials.
I want to have
Insufficient materials.
many jobs as I can. So that's gonna take a while. So we have, I think we have one
Flight
on
mode.
this side. This is the new one. Okay, only quick pen. So, just looking for power to the station. Already, they're all parked in the top. These are the vehicles that fly up. Inside we have those. Jet platform one. That's from one planetary logistic to an interstellar logistic. You can have multiple planetary logistics. This one just inputting from other planets. So I'm gonna need the little squares. This is how we get it. So plan is to solve this problem where I have to make inside this box. So the drop in so how can we start to someone? Power.
Flight mode.
So this is where power grid is. Spark.
Flight mode. Insufficient materials. Insufficient ma- Flight mode. Replication complete. Insufficient materials. Insufficient materials. Replication complete. Insufficient materials. Insufficient materials. Fabrication complete. Flight mode. Flight mode. Insufficient materials. Flight mode.
using the Delta 101, and then they get transported all the way to this part. Yep. Now we have continuous stream. Going on research. Success. Done. Next mission. Balance the power grid. It's loading.
Flight mode.
Gonna generate this.
Insufficient materials.
This is our resource production panel. It shows you production and consumption. I usually look at it at the same time. This is Proliferate is fine, it's okay. But production and consumption is fine, and that's gonna be a problem because that's gonna suffocate our entire holy shit. Hopefully I'm consuming more than producing the tanks back or at least upgrade.
Insufficient materials.
Let's see if we can upgrade this. If it's possible. Just upgrade these a little bit. We probably don't need additional ones. So what's the difference? Higher durability, higher production speed, higher work consumption, higher energy consumption.
Replication complete. Flight mode.
So we're upping our energy production. So cool.
Cruise mode. Cruise ended. Flight mode. Cruise mode. Cruise ended.
Then I'm gonna have to pull up there. Just set up. The code provider.
Flight mode. Cruise mode.
System. It's time to move now. We maybe just requesting it. It's gonna get stored. These vessels are quick. Where's the sun? Yeah. Rock.
That's right.
Let it go for Brian Green in
The
the house.
returning champion, Brian Green.
Thank you. Thank
Fan
you.
favorite, by the way. You know that,
Yes.
right?
Appreciate
Our
that.
fans love you.
That's great to hear.
We love you because you're a theoretical physicist.
Yeah.
And while, of course, data matter, people like just thinking in an unfettered way about what could be true
Yeah.
or not true about the universe. And there's so many things being bandied about lately, especially in the quantum realm, that we thought we'd bring you in for a special recording where there are no time limits on this. We're just going to talk universe. Everything cool, weird, and wacky about the universe.
Let's do it.
Nice.
And you're the man for it. By the way,
Yes.
when you're not here, I just sort of fumble over what I know, but when you're here, we got him.
Yep, exactly.
Okay, so let's remind people, your specialty, I mean, historically is particle physics specifically?
Yeah, I certainly came from the particle physics side, quantum mechanics, and then moving toward gravity, which of course is the other
Wow.
end of the spectrum.
Yeah.
Okay.
And that's what took me to string theory, which is this attempt to put them both together.
Put 'em all
We'll
together.
get there.
Yeah.
We're totally going to get there.
Nice.
All right, so that means there's no scale of physics that's out of your reach.
Well, I wouldn't quite go that far, but
You are kind of covering it all, man. I'm just saying.
Particles in the universe.
What else is left?
well, what's left are the complicated things,
Ooh.
like the brain, like the mind, like consciousness,
people,
like
yeah,
biology.
people.
You know,
Right,
so
yeah,
yeah.
okay.
We
You do
stay
the easy-
simple.
You do the easy stuff. The physics is
Oh.
the easy stuff. You've written multiple best-selling books.
Yeah, a lot.
And the one people remember most, perhaps, was The Elegant Universe.
Was that your first?
That was my first.
That was your first
yeah.
book?
And it was a runaway bestseller.
Yeah.
Yeah, for W.W. Norton. And your most recent book in 2020 came out just in time for COVID. Until the end of time.
Yeah.
Nice. Wow. that was
Fitting,
very
right?
very prescient of you.
Yeah.
If you were religious, it would be the end of days.
Right. The end of days.
So what I like about you is you have a breezy way with communicating your complex physics thoughts. And in no small measure, is that honed in books that are written for the public, A. B, you're co-founder, I think, with your wife, Tracy Day, former news correspondent,
Yes.
who
Nice.
interviewed me many years ago.
Yeah, yeah.
I think for NBC?
Could well. ABC. Yeah,
ABC, yeah. And Tracy Day co-founded the World Science Festival.
Oh, wow.
We did.
Yeah. Now that's just, initially it's just being badass because it was New York,
which is the world, though. I'm not sure if you realize this.
So I haven't attended as many of these as I have always wanted, but those that I attended, I thoroughly enjoyed the juxtaposition of the science and the art and the music and just science as culture.
Yeah, I
think
mean,
is
that's
what
the
that
point.
is.
I mean, much of what your work is about the same thing. People need to see science as part of the fabric of culture as opposed to something off there on the side that you are forced to take in school and then you leave it behind.
Right, you leave
Yeah.
it behind. And
Yeah.
so I think World Science Festival does that brilliantly. So
Thank
I just
you.
want to congratulate you
Appreciate
on
that. Thank
year
you.
in and year out. It's still going strong.
Yep.
So before we get to Cosmic Queries, because we poll our fan base, our donors really, the Patreon members, and like they all know you. So they're coming in with questions hot and heavy, straight in. And I worry that I might be asking some questions that they'd be asking.
Well,
Is that allowed?
yeah. So what?
Okay.
I mean, and for everyone that we come across that you have asked that they will ask because they've already submitted, you will just give us $5 because that's how much it costs to be a Patreon member.
At the entry level,
At the
you
entry
get
level,
question.
yeah.
Okay, so Brian, let's just right off the bat, we hear about the multiverse. Okay, on one side of a fence, and then you cross the other side of the fence, and then we hear about the many worlds hypothesis in quantum physics. Do these have anything to do with each other?
Yeah, they do. The idea of a multiverse is the umbrella concept for any variation on the theme where our world is not the entirety of reality.
Oh, so that would cover all cases.
That's
All
everything.
cases.
Oh,
Whether it's a
Yes,
multiverse
yes.
or not.
Yeah,
So
exactly.
the multiverse is under the many worlds.
Well, I'd say
No.
many worlds is under.
under the multiverse?
Yeah,
Under-
because the multiverse is the umbrella idea.
Okay, so the multiverse encompasses every single
And there
possibility.
there's something like 10 versions of many worlds that have emerged from radically different ideas, and quantum mechanics is simply one of those.
Okay, so I was mistaken to think that the more, dare I say, traditional multiverse descriptions, there's one where there's multiple bubbles within our space-time.
Sure,
or
that's the inflationary multiverse.
inflationary.
Yeah,
You
sure.
know, I'm thinking that's the multiverse.
I'm bringing it down, by the way. Inflation.
You bring it down.
Affordability. It's a hoax.
The universe is not really inflated.
It's not really inflated. It's the best price it's ever been. There's never been a better price in the universe. Oh, so anyway.
So, and then I'd learned many worlds when I first learned quantum physics.
Yeah.
Where you needed some way to get out of the conundrum that you're observing statistical phenomena.
Yes, exactly.
So catch us up on the many worlds specifically, and then tell us how that plugs into the multiverse.
Yeah, so when people developed quantum mechanics, this is now going back to the 1920s and 1930s.
The centennial decade
Yes.
of quantum physics.
Precisely, which is why I'm writing a book on it that will be published in this decade.
Oh.
But
You're writing a book to catch people up on that.
yeah, exactly.
Yeah, very good.
And the progression of the ideas beginning in the 1920s was to note that a particle, let me be specific, like an electron, it could be partly here and partly there, 50% here and 50% there. And the question was, but when you look and you measure, you always find the electron here or there. You never find it in a blended mixture being at two locations.
Okay.
And people scratched their head for a long time trying to
can
figure
imagine.
out how do we transition from a theory that describes a fuzzy haze of possibilities to the single definite reality when we make an observation or an experiment.
How much of that definite reality was a bias coming out of classical physics?
Well, you could say all of it
Yeah.
because our brains are big and we think they probably operate according to laws that are biased toward the classical, the big stuff.
Yeah.
And our
So classical
experience.
physics, there's an object, it drops, there's a thing, you
Right.
move it.
Right.
There's just stuff that kind of makes sense to
Yeah,
us.
exactly.
And nothing in quantum physics makes sense.
And nothing in experience suggests there's anything but one single definite reality. And that was the conundrum. Experience shows one reality. Quantum mechanics speaks of many
Many
possibilities.
And measurements in that realm.
Right.
That's right. So measurements in the realm of the small somehow seemed to pick out one singular definite reality. But here's the problem. When you look at the mathematics, which comes from Erwin Schrödinger, you can't transition.
Of cat fame.
Yes.
Yeah, cat fame.
No, there should
what a
have been a
shame.
Schrodinger's cat in the Broadway musical. I think.
Of
That would've-
cats?
Yeah, that would have been really cool.
Well, how
There
do you
wasn't
know, how
one
do
in
you
the
know there
other worlds.
wasn't?
And this is the point. So Schrodinger's mathematics forbids a transition from many possibilities to the single definite outcome of experience. And so people said maybe the transition never happens. And this is Hugh Everett, 1957 at Princeton. He looks at the equations and says, we are imposing a classical bias on reality.
Yeah,
we think there's a single definite reality, but according to the math, if you look at that cat, there's one universe in which the cat's alive and you see it alive and you're happy. There's another universe where you see the cat dead and you're chagrined.
Right.
And that's the true reality. Neither of you knows about the other version of you. Each thinks they live in a single definite reality, but the bigger picture embraces more than one world.
Was that other world always there, or was it created in the moment that they had
The realization of another
the
world.
realization
the
of
realization
the cat
of
being
it,
alive
the
or
cat,
dead?
right.
It's a really good and subtle question, and I don't think every physicist sitting in this chair would give you the same answer. As I look at the mathematics, I would say all those worlds, in a sense, are there. There's nothing really splitting, which is how we often describe it. The world splits into two. It's more that the description of the quantum realm allows
See his body language. Let me see some of that more.
I know.
I love that. Give me some more of that.
the mathematical description now allows us to use the language of one world or another when that language wouldn't have been applicable before your measurement. But it's not like the world splits and splits and splits. It's all sitting there in some giant uber realm.
Gotcha. So, does the realization of the measurement, are you saying that there's a possibility that you're not measuring a definite thing at that moment or instant, I'll call it, in that instant? Or are you just seeing that and everything else is just still there, but like you can't see it because you're looking at this?
See, it all depends on what you mean by you, and I hate to be so specific in the wording, because if by you have the conventional notion of a single human being,
Okay.
each version of me does see a single world, carries out a single measurement.
There
It's
it
just
is.
that if you had a God's eye view,
There it
which
is.
we don't have, you would see many versions of me with many outcomes.
Okay, that is so freaky,
Okay,
man.
but it sounds like you just pulled that out of your ass.
I didn't.
I assure you.
All right.
But that's an important point. Let me just emphasize that when Hugh Everett came up with this idea, it was the most conservative interpretation of the mathematics. Yes, it seems ridiculously uneconomical to have all these worlds, but the math, if you just take it at face value, this is what it seems to say.
Nope, that's lame. Ready? Do you harbor questions about the universe? Some long-held bit of cosmic curiosity lingering within you? Or questions about anything at all? You can become a Patreon supporter of Star Talk. You have